Welcome back to the series on X-ray powder diffraction. Amorphous compounds have been mentioned a few times in these, but now is a good time to pause and look at the nature of amorphous compounds as a classification. Any solid that is not crystalline is amorphous, but what does amorphous actually mean? In this scenario, any compound which can organize in such a way to avoid repeating units is amorphous. If they have a degree of hardness, then they are often referred to as being glassy or being a glass. The familiar glass used in windows is a covalent network of silicon atoms bound to bridging oxygen atoms. Each silicon atom tends to form 4 bonds, similar to carbon, but interspersed within the tetrahedral silicon centers will be the occasional silicon-silicon bond or silicon-oxygen double bond. In addition, there may be interspersed impurities which may or may not be intentional inclusions, also known as doping. The entire field of ceramics fits into this broad space, but let's keep this limited to our needs. Melting is when the temperature generates enough ambient energy to overcome the lattice stabilization of a crystalline material. As such, amorphous materials do not actually melt. However, there is a temperature where the glassy material transitions into a rubbery state, aptly named the glass transition. A rubbery amorphous material may have enough mobility on the molecular scale to rearrange the atoms into a different state and maybe even a more stable crystalline phase if one is available. This glass transition is significantly more nebulous than a melting point and is easily lowered through the presence of water, which plasticizes the material. The standard assumption is that for each 1% of water content, the glass transition temperature reduces by approximately 10 degrees Celsius. Amorphous powders also tend to have extremely high surface areas as they are not self-assembling into specific shapes, which also increases the potential for amorphous powders to have water adsorbed onto the surface. These two factors combine to create a bit of risk for any amorphous powders, which are intentionally generated to take advantage of different characteristics, such as increased solubility when compared to a crystalline phase. Solids with a glass transition within 50 degrees of an anticipated process or storage condition are considered at risk of potential recrystallization and are discouraged without desiccation. As more and more small molecule pharmaceutical drugs are exploring amorphous solid dispersions, it is crucial to consider these factors to minimize risk and optimize reproducibility.